Hello everyone, and thank you for joining me today for the latest in the LiDAR Processing webcast series. This is the fourth, and today we're going to continue the theme of editing and filtering LiDAR data that we started last time, but this time we're going to take a look at some of the automatic LiDAR reclassification tools. In our previous session, in the third session, we identified and demonstrated some of the manual processes that we can employ to change the classification of your LiDAR point cloud, to remove points that are not required from a geographic perspective. Today we're going to look at some of those reclassification tools, and this is going to allow us to demonstrate some of the more powerful functionality that comes with the LiDAR module. So specifically what we're going to look at is a series of automatic point identification tools, and we're going to start that process by looking at a fairly new tool, a more recent addition to the LiDAR module, and this is a function for identifying noise points. Noise points would be points that fall beyond what you would expect in terms of an elevation value. They may be low points or high points, and we'll go through a process where actually we will identify both. Some of our points are below our expected elevation threshold, some of them are above, and we'll take a look at that workflow. We will then take a look at what's probably the most powerful and certainly one of the more requested functions of our LiDAR module when we were developing this functionality, and that's our ground point reclassification tool. For this example, we're actually going to start with a point cloud that's entirely unclassified, and we're going to ask Global Mapper to identify within that point array which of the points are likely to represent ground. We'll go through the various settings you can apply to allow Global Mapper to interpret different geometric structures within your point array and come out with a reclassification. We will then take the same data, and those points that are still unclassified, we will identify points within that point array that are both buildings and what we define as high vegetation or trees. So this will allow us to isolate building points based on their geometric characteristics, and also to identify vegetation points. The final workflow that we're going to go through today is one that we've developed specifically for looking for power lines or utility lines, and this is a fairly straightforward process. If you have a linear point cloud or a point cloud following a linear feature, identifying those linear patterns in that point cloud allows you to reclassify them based on this power line classification. Now, the reclassification is a means to an end. In the session that will follow, the next presentation, we're going to take some of these reclassified points and actually do some vector extraction. That will be next time, but for today we'll focus on this reclassification process. So in this first example, we're going to take a look at what's a relatively small point cloud. We have just under 1 million points. This happens to be a little bit north of where I'm sitting right now, the city of Augusta, which is our state capital here in Maine. And we're looking at an area of the Kennebec River and the city on either side. Now, a glance at this point cloud would immediately tell you that there's something that we need to address, because you'll see right here within the river we do have some returns. Now, I happen to know that this section of the river is fairly shallow, so a lot of these returns, a lot of the point returns we're getting are actually from the riverbed as opposed to what we would consider to be water returns. And we can verify that a couple of ways. I'm going to actually show you a couple of different views of this data before we actually get into identifying or to going through the noise identification process. I'm going to use our profile tool first. Now, we've introduced this in one of our previous presentations, a method for visualizing your point cloud from a cross-sectional perspective, and you can define the width of points that you're looking through. I believe in this case I'm going to be looking at a 10-meter wide swath. So I'm simply going to left-click and right-click through the center of through the river channel here. Now I'm going to pull this up a little bit so we can see what's going on. It might be difficult to see, but if you look at the elevation scale along the left side of this profile window, you'll see that we have a value of 0. That would be what we would assume to be sea level. And you'll notice that in the river area, those points are, as you would expect, below that level. If I was to embark on any process whereby I was identifying ground or building a ground model, we know those points would not be points that we'd want to use. So as an initial step in this process, we would want to identify points that fall outside of our threshold. Now in this case, obviously, I would filter based on a value of absolute 0. So memorizing that, knowing that that's an issue, we will apply that in the noise dialog box that we'll see in a few minutes. Also in this point cloud, and this is something we detected after we chose this as an example, which is another interesting one, if I view this in 3D, my 3D window is just off screen. I'm going to bring it back into view here. Might be difficult to see, but right here where my cursor is located, you can see a hovering point. I think there's actually a few points right in this area. There's a little red point right there. Now, obviously, that's not something that we are interested in as far as any ground modeling or even feature extraction is concerned. My assumption is that this is probably a bird. When the aircraft was flying overhead, one of the laser pulses happened to hit one of the birds flying underneath and got a return. So that again would be defined as noise in this context. Obviously, a very extreme case of noise, but something that we would want to address. Now, if we wanted to, we could address this in our profile view and manually delete it, but we will first go through the process of identifying noise so we can show you that process. So the noise reclassification is one of our LiDAR module buttons. Now I've actually undocked the LiDAR module toolbar. We're going to focus on a number of these buttons during our workflows today. So just bringing them down from the toolbar itself so we can see exactly what we're looking at. Now the first button in this toolbar is our Auto Classify Noise Points button. We're going to select that, and it brings up a dialog box that lets us define what we would categorize as noise. First setting we can apply here is a setting that will allow us to determine the number of standard deviations from the mean to identify as noise. Now we have set as 2. I'm actually going to edit this and bump this up to 3 just based on this point cloud. Outside of that, we can determine what to do with the points that we identify as noise. If we check this box, those points will automatically be removed from our point cloud. They will be deleted. Knowing how Global Mapper works, they will not be deleted from the source file, but they will be deleted as far as Global Mapper's visualization is concerned. Now, that's kind of 2 steps in one: identifying noise and also remove them. In order for us to see the results of this process, I'm actually going to uncheck that box, and we will see the noise points based on a very specific color as that will be assigned to that noise classification. Now, when it comes to actually identifying the threshold values, we can do this in a couple of ways. We can do this based on the variation of the points based on our known ground elevations. I'm actually not going to take that approach in this case. I'm going to uncheck that box, and instead I'm going to do the noise identification, perform the noise identification based on absolute 0. Now you'll notice when I check this, these fields are pre-populated, and these numbers represent the extent of the elevation values that are in our point cloud currently. So there obviously is a bit of a problem here, because we have at least one point that's minus 24 meters. I happen to know that here in the state of Maine we don't have any ground points that would be below what we'd consider sea level, so that's something we would have to identify. Also within this area, I believe the maximum height that we're looking at is about 70 meters. Let me just check some of my notes off screen to make sure. I think about 70 meters is the highest possible point. This is approximately sea level, as we saw in our profile. So obviously a point that's almost 500 meters is incorrect. This is probably one of our birds. What I'm going to do very simply is establish my range of 0 to 70. And again, this is based on absolute as opposed to height above ground. Couple of other options in here before we actually perform this process. We can identify noise points from those that are already classified if we want. That's what we want to do in this case. In other words, some of the points that were within the water area were already identified as ground points. I want to make sure Global Mapper addresses those in this process as well. And if necessary, we can reset all of the noise points that have been previously set, and we can go through this a couple of times, I guess, to get the results that we need. Each time we can reset them to unclassified before we begin. There are various filtering options to limit the extent geographically, or to limit it based on a number of the filtering options that we talked about last week as well. We'll leave the other settings as they are. I'll click the OK button. Now, you'll see, quick dialog box, we went away. This is a small point cloud, so we're seeing the results very quickly. Nothing immediately apparent in this view. If I change my visualization to visualize by classification, I'm going to see, in this case, we already had ground points, we had unclassified points, but we now also have an array of red points. These are identified now based on my threshold values as my noise points. Once again, using my profile tool, drawing my profile line, you can see very specifically underneath that 0, everything that's underneath 0 is now classified as noise. There are additional noise points as well that are outside what would normally be expected within that area. Let me again bring up my 3D view, and hopefully we can identify that point, which again you'll see it's red right here, and that once again indicates that it is a noise point. So if you recall, in this workflow, we didn't remove the noise points, we simply flagged them. And it's a good idea to do that before you actually remove them. There may be some changes you need to make to some of the settings before you actually apply this permanently. But now that we've established these noise points, we can go into the filtering dialog box. We can take our noise, our low point noise, and our high point noise as well, and disable those. I'll use the low point noise for now, and you can see all of those low points are now removed from the point cloud after having gone through an initial QA to see if that's exactly what we wanted to identify. So that is automatic identification of noise points and ultimately filtering your data based on that. So in this next workflow, we're starting with a point cloud, as I mentioned before, that's entirely unclassified. Now, those of you who are using some of maybe the LiDAR point cloud data that you've acquired from USGS or some local government agency, this is an unusual situation. It's more likely you will actually have some classifications already assigned to this point cloud. So we're kind of starting from an extreme situation. This is useful for those of you who are maybe working with point cloud data that's not natively LiDAR, maybe photogrammetrically generated point cloud data for which there is no inherent classification. So I use this example to show you can begin with literally nothing, with literally X, Y, and Z values associated with these points, and based on the geometric characteristics of this point cloud, automatically identify ground. And that's ultimately what we're going to do now, is we're going to transform some of these, what are unclassified points. We have about 1.5 million, just 1.6 million points. We're going to find out which of these points are likely to be ground. Now, before we begin this, what I want to do first is actually turn on my legend. I just opened the configuration dialog box. I'm going to go to my display options section, and we have a map legend section here. By default, there will be no map legend displayed. I'm going to change that. I want to base this on my loaded vector types. We know LiDAR is vector, so that will allow me to display a legend based on the different classifications that are currently present. I'll just call this class as a header, and if we needed to change any of the other settings, we could do that based on the font size, etc. I'm not too concerned about that right now. The legend by default will appear right here in the bottom corner of my screen. That's perfectly fine for this situation. Click OK, and just confirmation that we have a class and it's a single class, unclassified. So the process of identifying ground is another button that's accessible in the LiDAR module toolbar, and actually the second one in this array. When we select it, it brings up another dialog box, and just a couple of settings we need to apply here. The first is the bin size to check for curvature deviations. What this means is basically Global Mapper wants to look for points that occupy a defined surface. It's looking for variations, and this bin size reflects the extent of that sample area. Now, there's a couple of different options in terms of defining that extent. It can be either based on an actual unit of measure, meters in this case, as you will see, or based on a variable based on the average point spacing. Now, this is a useful one because depending on the resolution of your point cloud, you may not need to sample quite as many points. A physical unit of measure or a ground unit of measure may be overkill in certain situations. So a variable based on your point spacing sometimes is the best approach. In this case, I'm going to choose a variation of 5 times my average point spacing in this layer. Let me pause briefly. One of the questions we're very often asked in introducing or demonstrating this functionality is, what are the best settings to use? That is an impossible question to answer because every point cloud is going to be different. The geographic area that you're looking at is going to be different. So there is no one-size-fits-all approach to this. My recommendation, and this goes for many of the questions we're asked in Global Mapper when it comes to defining some settings, my answer typically is, try the certain settings in a very small subset of your data where you know what the results should be, and maybe vary some of those settings. See where you get to a point where the results are optimized. Once you get that for a small subset, you can go to the extent of your data and apply the same settings, confidently knowing that it is what you saw in that representative sample would be have the same quality over the full extent of the data. So in this case, that's exactly what I did. I did some testing. Optimized point spacing in my case for this point cloud is 5 times the average point spacing. The second setting here allows me to determine a threshold value. After Global Mapper finds that base level surface based on the geometric properties of the points, it will allow me to establish a threshold. Now I have to say, because this is a fairly low resolution point cloud, I'm going to extend this a little bit more than I would typically do. This is a 1 meter threshold. We use this for effect so we get some results to actually show you. If you want to keep that tighter within the extent of the area that we've defined above, we can vary this by 10 centimeters, 20 centimeters, whatever you need. The lower that value, the fewer ground points you're going to get, but the more precise the ground model. So it's a little bit of a trade-off here. Again, in this case, just for the purpose of demonstration, I'm going to keep this as 1. Moving to the final 2 settings, these settings allow you to define what the expected height delta and expected terrain slope are within your area. If you're working with a relatively flat area, you can get away with using a smaller value, and this will allow you, Global Mapper, to identify points that are outside of that range that it will completely disregard when it comes to trying to identify ground. Also, points that occupy a surface that's inclined more than you would see typically in that area. Again, those will not be considered ground points based on the value you put in here. Once again, same options for filtering before we embark on this process, and once again, options for resetting what are your existing ground points to unclassified before you start. I should say, by the way, while we're performing this process based, as I mentioned before, on an entirely unclassified point cloud, you can improve existing ground points using the same process. So with the points that remain unclassified, you can go through the process a second time perhaps and bring in some additional ground points, or again, based on an off-the-shelf point cloud, add more ground points to the ground point total, ultimately improving any ground analysis you're doing further down the road. So with these settings attached, we will hopefully see a visual change. One of the additional filtering options that happens automatically, if you look very quickly, you might actually see this noted in the status bar that will appear in just a second, but it basically is a filter that will only acknowledge the final return for every pulse. We would have to assume that a first of many return, or first of 2, or first of 3 return is not likely to be ground. We tend to find that LiDAR does not penetrate ground, so it's unlikely that a second of 2 return, or a first of 2 returns is going to be a ground point. So you may see that noted in the status bar, as I mentioned. We'll click OK, and there we can see the results immediately. We can see now we have an additional item in our legend, our ground points. So we can see obviously very clearly on the map those points that are ground have been reclassified automatically. If we go into the metadata for this particular layer, which we can do by right-clicking, choosing metadata, or double-click M, we will also see that we now have about half, almost exactly half of the points that were previously unclassified, or just as many unclassified, are now ground points. So if we were embarking on a procedure to do some sort of ground analysis, perhaps contour generation or any other terrain-based analysis, we now know we have a fairly sizable number of these points that can be used for that purpose. I chose an area, by the way, for this particular example that has a good selection of different types of environment. We've got obviously a heavily forested area here. We've got a suburban area, got low density residential. So we're kind of challenging Global Mapper to identify ground points in each of those situations. To quickly visualize, once again, I like to use my profile tool to see the results. Drawing a profile line through one of the forested area, we can see very clearly that the ground points have been identified. People often look at this type of pattern, by the way, in the bottom left corner, said, well, ground obviously is extended, but remembering we're actually looking at a swath of points here, so you're actually looking through 10 meters worth of points, so that's why we're seeing variation on that linear path. It's not a flat line. Fairly defined flat line here, so we know this is looking laterally through the terrain. This is a flat area. So I now have ground points. Obviously, our tree points are still unclassified. Looking through the residential, the urban area, we can once again see our building roofs are still unidentified. A little bit of an anomaly here. We can see some ground points for some reason were identified here. We may want to adjust our angle threshold to identify that what happened here. There is one very significant error, and that's another reason why we use this example. Right over here, this is a big box store. This is a store, I believe it's a hardware store, occupying many hundreds of square meters. Because of the geometric structure of the roof, Global Mapper thought it was ground. I'm actually going to address that one as the final step in this workflow a little bit later, how we can override the default classification. But obviously something went wrong here. This is an example of why this is not a perfect science. So ground point identification, very significant part of the LiDAR module workflow. So the next workflow, the next automatic classification workflow, is actually going to be continuing with this data. We've obviously in this workflow identified ground. There are still a significant number of these points that are unclassified, and what we're going to do next is identify those and try to determine what the characteristics of the surface is. Now, specifically what we're going to look for in this initial workflow are building points, and it's quite clear to see we should get some results very clearly defined with these large buildings, but we're also going to identify vegetation points. Again, heavily focusing down in this bottom right corner, we should see a significant number of vegetation points here. We'll keep our legend open so we can see the results of this in just a second. And these two functions are actually combined into a single process. The algorithm that identifies buildings and identifies vegetations is basically the same process based on the settings that you'll see in just a second. Now, I should stress, if your intention is to use LiDAR for ground analysis or terrain analysis, you don't need to do what I'm about to do. You've already achieved what you want to achieve through the automatic reclassification of ground. You can simply filter out the non-ground, leaving the ground points, and continue with whatever that process is. What we're moving towards now is a first step in the process of identifying features within a point cloud, specifically buildings, and as you'll see in our next session, we will actually extract those as vector features. So once again, a button in our LiDAR module toolbar. We're moving on to the third button here, Auto Classify Non-Ground Points. This has actually got two different functions, and I'm actually going to hold off on the final option. This is the last workflow we'll do today. I'm going to address specifically the procedure for identifying building or high vegetation. Settings we're going to apply. We're going to look a little closer for our building points. We're going to keep this as a single value of a 1 times the average point spacing to look within our unclassified points for buildings and vegetation. Now, the parameters that we establish, I'll go down through these individually and describe what they do. Once again, there is no one size fits all. There is no, the values I'm using for this scenario were derived very specifically through trial and error to make sure the results were what I would expect to see. And I used a small sample of my data to determine what these should be. So don't think that these are the do-all and end-all for every situation. The first one is a fairly obvious one. Based on the remaining gray points, those remaining unclassified points, of those, which do we want to analyze to be possible vegetation points, high vegetation specifically, or buildings? Well, this value obviously allows us to determine that vertical offset, vertical threshold. I would assume that most buildings are at least 2 meters tall. They're maybe some shorter ones, I don't know. That's your call. And indeed for vegetation, we're not interested in this example identifying low vegetation, bushes, etc. We want to identify trees in this case. So establishing that vertical threshold allows us to do that. In other words, every unclassified point that is less than 2 meters above the local ground that we have previously identified will be ignored. By the way, I should also say this process will not work if you do not have ground points present. it needs those ground points in order to determine these threshold values. So you'll get a warning if you try. If you try to start with unclassified data or data that has no ground, it will say you need to at least identify ground first. So 2 meter threshold. The second value here, this maximum coplanar distance, is specifically intended to look for building planes. Now, in this case, buildings we would assume to have a flat surface, either a horizontal flat surface like a retail store perhaps, or maybe an inclined flat surface like a normal residential building with a pitched roof. The process of identifying which of the points correspond with those types of structures is based on this coplanar modeling process. Points that occupy a plane surface. We know the threshold value is above 2 meters already. We've already established that. But within those remaining points, those that occupy a defined plane, and the variation, you say, the variable here is 0.25, which is 25 centimeters. Any point that's within 25 centimeters of that coplanar surface will also be considered a building point. So that 0.25 is basically a threshold value above or below a calculated plane surface. For vegetation, we can just determine a minimum offset. Now, we would assume that most vegetation points do not occupy a surface. Vegetation is a tree is a fairly random structure. So we can establish a minimum vegetation distance. This is the offset threshold so that adjacent points would be considered would be considered vegetation. Obviously, this considers the relationship, the geometric relationship of points with the neighboring, with those points that are within the immediate vicinity. So this minimum vegetation distance, and again, trial and error in my case, 0.4 meters is what I've established here, 40 centimeters. The final setting we're going to establish is a max coplanar angle difference. Now, going back to our surface models, our building coplanar models, if there is a situation where Global Mapper identifies two plane surfaces, two coplanar surfaces that are within a 5-degree variance of each other, that are abutting and are within that 5-degree range, we would, the algorithm assumes they're part of the same surface and will consider those therefore to be building points as well. So this again allows us to establish that coplanar angle threshold based on multiple abutting surfaces, 5 degrees in my case. You'll see we have an option here to apply power line classification. I would suggest if you have power lines as well, consider this as a separate process. Very seldom will you actually go through both at once. What I'm going to see as a result of this process are 2 additional colors on my display. We will come back in the final workflow and address the power lines. Once again, filtering options based on geographic extent, based on any of the inherent attributes within your data, and you can remove the points that you don't need. And checking my values here, I'm going to click OK. And once again, status bar indicating that it's working through the process. And hopefully we will see the results. As you can see, we now have very clearly defined what are our vegetation points. We have points that are not only these big box stores, these large retail stores identified through a solid flat surface, but also our residential buildings, our houses, which obviously would have pitched roofs. I think we can actually see that. I'm going to draw a profile line, and we should see not very clearly defined here because of the angle of my line, but obviously it's identified those as buildings as well. And you can see a tree over here on the left side. Do another profile quickly through my forested area, and this is very clear to see this random distribution of points above our 2 meter threshold, very clearly defined as vegetation. Now, what we haven't done here is identify individual trees. What we've simply done is taken all of our points and assigned a classification. In fact, if I use my feature info tool now, we can confirm that. I'll just choose a point at random. That point is a class 5, and we can actually, if you're not sure what your classes are, let me close the dialog box. Easiest way to find out, go to your filtering dialog box, and you'll see that point is high vegetation. The vegetation extraction, by the way, is only high vegetation. We do not have an algorithm for identifying lower vegetation. So all of the points that are identified as vegetation points will be high vegetation. So before we close out of this workflow, this is a little bit of a kind of a recapping something that we did last week, where we need to manually override one of the results here. I pointed out previously, we see this building, obviously incorrectly classified. Now, through a little research, I figured out why this happened in this particular example. If I use my profile tool, I'm actually going to extend the extent of the profile, extend the width of the profile. I believe 45 meters in this case. This is based on what I did done previously. I'm going to draw a profile line right through the middle of this building. In fact, I'll zoom in a little closer. Actually, before I do that, you may actually see why this problem occurred. Here you can see on the roof of this building there are what I learned are actually air conditioning ducts, fairly large structures on the roof. Because of that geometric pattern, Global Mapper made the assumption that the points that surround those air conditioning ducts are actually ground. So it made a correct decision in the geometric pattern, but obviously in this case that is not accurate. So how do we rectify that? Well, we could simply select all the points within this area and manually classify all of those points. I don't think that would give us the results we need, knowing that there are points on the roof that are not part of the roof line. They're part of those air conditioning ducts. So we do not want to reclassify those as building. So what I'm going to do instead is draw a profile line through the center of that building. Simply left click, right click, and again, in my case it was 45 meters wide. That's why I established when I right clicked. And we'll see now the array of brown points. Now we're obviously getting a lot more here. We're getting a little bit of extra points in here because there must be a tree right next to the building. Remembering we're not looking at a single linear path, but we're looking at a 45-meter wide swath of points. So we're actually picking up some data that's outside the extent of the building here, these green points. You'll also notice that the roof line itself is not flat. I'm looking at my scale, there's probably about a 2, maybe meter and a half range of elevations here in this roof. Well, while the roof may look flat, it's actually not. The roof designers would have designed it to allow runoff. So that's why we're seeing a range of values here. But what I'm going to do in this dialog box is quite simply select the points in this extent and reclassify them manually. I'm going to do that in such a way that I will not choose the points that are above the roof line, obviously, or below the roof line. I can very specifically choose those that occupy just this area. And we use this drop down to choose the tool. We can drag to select, or we can create a polygon. The polygon would allow us to select based on an irregular shape. In my case, the drag to select will work fine. So I'm just simply going to choose, with not too much care, but I'm just going to quickly choose all of these points that occupy what I consider to be the roof. You'll see they're selected, and this allows me to use one of these shortcut buttons that we've seen in the standard LiDAR toolbar. In my 2D view, we also have these in the profile view. So we can perform edits right here in this cross-sectional view, and I'll apply the classification building to these, and confirmation that about 5,391 points have been reclassified. And we'll see that result immediately in this view. Close the window. Points are still selected with my digitizer in the 2D view, so let me just hit my escape button, and once again we'll see those points reclassified. Now if you look again very closely, you will notice that there are little gray dots in here. Those are the points that are still unclassified. Now if I was to perform a building extraction process based on these remaining points, it would not factor those gray points, which again are our air conditioning ducts. While we're in this area, we can point out another anomaly. And again, the only way to override this would be a manual override. Here, where my cursor is located, quite clear to see this is a bridge, an overpass. This happens to be a highway, interstate highway, and it obviously goes over a road. Now, based on the categories and the algorithm that we ask Global Mapper to follow, this occupies a surface that's above our 2-meter threshold, so Global Mapper made an assumption that this is a building. It is not. I'm not going to perform that edit in this case, but we could just simply manually override these. I would suggest leaving them unclassified. They do not represent ground. They do not represent buildings, so they would not be part of our building extraction. So you can override that manually. So again, a couple of different tools for applying additional intelligence to your data. Final thing I'll show you, sorry, I meant to do this after we finished, is going back to our statistics and high vegetation. Fairly sizable number here. We have a very forested area that we're looking at. Our buildings, we've got very few unclassified points remaining. So we've actually been able to take what was 1.6 million unclassified points, and all we have left is about 80,000 points that we don't know what the feature is. So Simply that reclassification allows you to improve the quality of your point cloud data. And if this is the end of your workflow, you could simply export this to a new LiDAR file, a LAS or LAS file. So in this final example, our objective is to identify within a point cloud above ground linear features, power lines essentially. You can use this for electrical cables, for maybe telephone cables as well. Obviously a linear feature like that, a power line, is a very small surface area. So in order for this to be effective, in order for you to get the results you need, you will need to be using a higher resolution or a higher density point cloud than we've used in the previous scenarios. In this example, if I quickly take a look at the metadata, you'll see that I have about 45 points per square meter. Significantly higher resolution than what we had used previously, which is approximately 2 points per square meter. So this is going to give us the raw material to get more effective results from this power line extraction process. This particular power line, obviously, this point cloud follows a linear path along our power lines. I have already identified ground points in this particular example, and you can see that probably more clearly if I generate a profile line. Right down below, I'll just drag this window up just a little bit. I've docked my profile view in this case. You can see my ground points are already classified. They're brown. Everything else, including low vegetation, my pylons, and the power lines themselves, are still unclassified. The objective in this exercise is to identify the linear patterns in these above ground points and automatically reclassify those as power lines. Now I'm going to turn off my profile view. I'm going to right click. We'll clear the profile. And we'll begin the process of identifying those point clouds. Let me actually select my zoom tool to zoom in just a little bit here, and we'll take a close-up view, and that way we can, oops, try it one more time, and we can identify just the points within this area for this example. The workflow begins with the same dialog box that we used previously, auto classify non-ground points. In our previous example, we had identified buildings and vegetation. We're making sure that box is unchecked this time. This time we're going to identify power lines. And the settings are obviously unique to this particular workflow. The minimum height above ground allows us to establish a threshold value below which the points will remain unclassified regardless of their geometric structure. So as I've said in the past, trial and error is the best way to identify these. Sometimes even looking at that profile view, as I previewed a minute ago, will give you an indication as to what that minimum possible height above ground. Now this is not absolute in this case, this is height above ground, and in our case we're going to keep this as 3 meters. Minimum distance from best line allows us to establish a threshold around a recognized linear pattern of points. So if Global Mapper identifies a line, basically a linear array of points, we can tell it to look for points that are 0.25 meters or 25 centimeters from that line and assume that they're also a power line point, and it will reclassify those as well. Our bin size to check for linear points, in this case it's going to be a meter value. Because of the density of our point cloud, we know it's 45 points per square meter. We're going to keep this as 1. It's obviously going to give us pretty good results even at a 1 meter sample area. Finally, we can define what we would expect to see in terms of height change per horizontal meter. I've kept this pretty high. Again, you can vary this based on your individual situation, but I'm allowing points that are 4 meter or 40 centimeters, I should say, below the starting point based on a horizontal meter, and that gives us a little bit of a flexibility in terms of identifying our power line points as well. So with these settings established, I'm going to change the bounds from the default in this case. I don't want to identify the power line points in the entire point cloud, so I'm going to specify the bounds as being just the data that's currently on my screen. We'll click OK. Click OK once again, and it will go through the process of identifying. You'll see it's first of all calculating height above ground. That's a prerequisite. Every point now has a height above ground value. Now it's going into those points that are above that 3 meter threshold and finding those linear patterns and ultimately reclassifying them. So saving my changes. From the top-down view, when it refreshes, it doesn't appear that anything has changed. If you look very closely, you may see a couple of yellow points interspersed within the other points. Now, the simple reason for that is having gone through that process, there actually are not that many points in a relative sense that are power lines. Most of the points in this point cloud are still ground or unclassified. And to verify that, once again, we can go into our metadata and we can look at our statistical breakdown. And of the 20 million points, only about 500,000 in this area were identified as power line points. So it's a fairly small percentage. In fact, you can see the percentage. 2% of the points in this case, just 2.8% are identified as power lines. So that's the reason we're not seeing them from this perspective. What we can do once again is use our profile tool, and hopefully this will make them a little clearer. Just a small section once again. Looking down below, you can see the linear pattern of points reclassified. You'll also notice that we have points within the pylon here that follow the patterns that we defined in those settings. They can be easily changed here. Simply select and edit them, make them unclassified if necessary. You can use your edit function right here in the profile view to remove those points that are not part of your linear pattern. So that's just another example of reclassifying points within a point cloud using an automatic process. As I mentioned, the 3 different variations on that theme are the first step in a broader workflow, where you would obviously, as a final process, maybe extract these to vector features. We're going to leave that one to next session. We'll go through the extraction process in our next webcast. So as I said during the introduction, basic theme of today's presentation was introducing some of the automatic classification tools. Noise point recognition, the ground point, which is probably the most useful one for most users, and then buildings, trees, and as a separate process, our power lines. If you have any questions on any of the functions I showed you, by all means send an email to our folks in our tech support team, geohelp@bluemarblegeo.com. If you're interested in a purchase of Global Mapper, perhaps you want a quote for your company, orders@bluemarblegeo.com is where you can send your email. And if you're looking at this video as a non-user, we do encourage you to take a look at Global Mapper. You can download a trial. It's a 2-week trial. You can also activate a trial of the LiDAR module as well. The information on how to do that was in our first LiDAR processing webcast, so take a look at that. Certainly, by all means, download a copy and see if it will work for you. As I said, next time we're going to take a look at the extraction process, so we look forward to speaking to you then.